Hello everyone, welcome to today's discussion on quantum theory. Today we're going to be describing the history of the key experiments in the history of quantum mechanics, the EPR Paradox, and something called Bell's Theorem. So don't worry if these sound very intimidating. I'm going to try my best to explain as much as I can all these concepts and experiments using as little physics and mathematics as possible. There will, however, be some mathematics when we discuss Bell's theorem towards the end, which is kind of unavoidable, unfortunately. But I'll try my best to explain it without using anything beyond high school level mathematics. So to begin, we're going to describe an experiment first proposed by the physicist Otto Stern in 1921, and then conducted in real life in laboratory settings by Walter Gerlach in 1922. So collectively, we will refer to them as the Stern-Gerlach experiments. So in the first Stern-Gerlach experiment, classical mechanics prior to the Stern-Gerlach experiments predicted the following. It predicted that if you were to take a bunch of silver, which is represented here in an annealing oven, which is a very, very hot oven, it's represented here by the periodic table name Ag. So you have a bunch of silver that's placed inside of a really, really hot oven, heated up to about 1300 degrees Celsius. And it turns out that when you do this, electrons will start being emitted. And so you can see on the side of the annealing oven, we have this little tube sticking out, which is the part of the annealing oven where electrons from the silver atoms are going to be emitted. And in this experiment, what we're going to be doing is we're going to be testing what's called the intrinsic angular momentum of each electron as it passes through an inhomogeneous magnetic field through what's called the Stern-Gerlach apparatus, which is those up and down arrows that you see. So those up and down arrows are not arrows. They're supposed to represent magnets. And so the idea is that you can measure the intrinsic angular momentum by measuring its deflection, that is the electron's deflection, along a certain direction. So in this case, we're measuring the z direction. The z direction is referring to the vertical component of the spin. So the classical expectation is that the distribution of electrons as spin would be roughly continuous. That is, you'd get some that are deflected upwards, some that are deflected at slightly lower angle, some going straight, some going slightly down, some going really far down. And so that's why I've represented this graphically using a phosphor screen with a bunch of horizontal lines on it, as you can see in the top left diagram. But it turns out that the classical expectation is false. It turns out that if you actually do the experiment, you get the surprising result that the spin of the electron is quantized. That is, the spin is exactly going to go head straight up or straight on down, as you see from the top right diagram. So the actual result is very different than the classical expectation. Okay, so suppose that we're going to do something called repeat measurements. So look now at experimental setup number 2, and suppose that, again, we have silver in an annealing oven heated to 1300 degrees Celsius. Electrons are being emitted out the side through an inhomogeneous magnetic field, and they're going to pass through the first z-axis Stern-Gerlach apparatus. So here we're going to isolate all the ones that are measured to be z spin up. So you can see that there's a 50% probability of the electrons being shot z spin up and 50% probability of them being shot z spin down. That's just an experimental fact that we observe in the laboratory. What's interesting is that we can isolate all the ones that went z spin up and then take a repeated measurement, that is, take a second z spin measurement. And it turns out that in accordance with common sense, if you measured something once and it had a result, you're also going to get the same result if you measure it a second time. So in this case, the z spin up electrons that pass through the first Stern-Gerlach apparatus continue being measured z spin up, as you can see in the sequential measurements. And analogous results also hold if you were to isolate all the z spin down electrons, as you can see at the center right diagram. So here we've isolated all the z spin down electrons, and they're going to continue to be measured z spin down at the next z-axis Stern-Gerlach apparatus. So now we're going to measure in experimental setup number 3 what happens if we measure the x-axis direction. So when it comes to the x-axis direction, here we again have the usual setup with the annealing oven and silver being shot out. And in the x-axis direction, we're going to get a 50% probability of the electrons being measured x spin to the left and x spin to the right. Okay, so that's just an experimental fact that we find. After all, the distribution of those electrons entering is going to be randomly distributed with respect to their spin. And again, just like in experimental setup number 2, we can isolate all of the electrons that were x spin left, which is what we're going to do right here in setup number 3. And then we're going to do repeat measurements. So the repeat measurement is consistent with what we see in experimental setup number 2. That is, x spin left electrons will continue to be measured x spin left at repeat measurements. And analogously, you can see in the bottom right-hand corner, the same also happens for x spin right measurements. That is, repeat measurements produce exactly the same measurement results. So far, nothing too strange has happened. Things start getting kind of strange when we combine x and z-axis measurements. So consider the following scenario in scenario number 4. Again, we have the usual setup. We have a bunch of silver Ag heated up to 1300 degrees Celsius in the annealing oven. Electrons are being emitted out the side. First, as you can see from the diagram, we have an x-axis measurement. So here again, 50% probability going left, 50% probability going to the right. Suppose we isolated all the ones that were heading to the right. We have a second x-axis Stern-Gerlach apparatus that in turn tries to double-check the x-axis measurement from the first measurement procedure. And again, you get what you'd expect. You get 100% probability of the ones that were initially measured to be x spin right also being measured x spin right again at the second measurement procedure. At the third level, we have a z-axis measurement. So because, again, the Ag, that is the silver, entering the initial causal chain here was randomly distributed with respect to spin, you'd expect its z-axis measurement to be 50% probability to be in the z up direction and 50% probability to be in the z down direction, which is what we observe. Okay, so far this is all consistent with the previous experiments. Where things get very strange is when you introduce a third x-axis Stern-Gerlach apparatus. So here, as you can see at the fourth stage in our causal chain, we have it that the information from the first x-axis measurement, that is, the first x-axis measurement isolated the ones that were going to be x spin right, this destroys the information. That is, the third x-axis measurement result destroys the information that we gathered from the previous two x-axis measurement results. And the reason for this is that x and z-axes, also this applies to y-axes as well, any kind of orthogonal measurements, that orthogonal measurements are such that the more precisely you measure one set of measurements, the less precisely can you measure the values of the other orthogonal set of measurements. So here, the more precisely you can know the x spin, the less precisely you can know the z spin values. And as you can see from experimental setup number 5, exactly analogous results hold for the z-axis measured first, then the x second. So in this case, usual setup, bunch of silver inside the annealing oven, electrons are shooting out. We pass it through the z-axis analyzer. We isolate the ones that are z spin up. We then pass it through an x-axis analyzer. We isolate the ones going x to the right, so that is they were z up and now they're x to the right. And it turns out if you try to measure the z-axis again, that information gets destroyed. And we have a 50% probability of the initially measured z spin up electrons now being 50% up and 50% down. Experimental setup number 6 adds even more complexity and confusion to the situation. In this example, we have, again, the usual setup with silver in the annealing oven. We have first an x-axis analyzer. We're going to isolate all the ones that were measured to be x spin to the right. Isolating all the ones that were x-axis spin to the right, now we're going to put them through the z-axis analyzer. So in this case, we're going to get 50% probability of measuring z spin up and 50% probability of measuring z spin down. What's different about this experiment compared to the previous experiments is that we're going to introduce what can be roughly idealized as like a wall. And I say idealized because I'm idealizing very much the exact contents of the physical experiments that have been conducted in actual physics laboratories. I'm just trying to ease explanation by simplifying a few things, but it still communicates the key empirical data. So in this case, when the original x right measurement electron enters the z-axis analyzer, we have a 50% probability of the electron taking the top trajectory. That is, you see this upper triangle here, where it bounces off the north wall, that is the top wall. And then a 50% probability of it instead being measured z spin down and bouncing off of the south wall. And so here, what's really key is that we're going to recombine both possible trajectories just before it enters the second x-axis analyzer. So it turns out that when you recombine the two possible trajectories, that the x-axis result you get is actually preserved. And the x-axis result that we get in this particular case is 100% probability measured x spin to the right. So just going over that one more time really quickly, for experiment number 6, we have a randomly distributed spin electron coming in. We isolated all the ones that are x spin to the right. Its z position could be z spin up or z spin down. It doesn't make a difference. It turns out that either trajectory that is being taken, and if it passes through the X analyzer again, we will measure, so long as that there's no interference here, 100% probability measured X spin to the right. And as experiment 7 illustrates, this still holds even if we shoot single electrons through. So this just shows you the unique causal trajectory of a single electron. So as opposed to there being a beam of electrons being shot through, the experimental situation still holds. That is, you get identical empirical data to that of situation number 6, even firing just a single electron one at a time. And even though I've illustrated in example 7 that the electron went x spin right, z spin up, and then x spin right, it is still consistent with the data that, for example, if you were to measure a randomly spun electron that goes through the first X analyzer, and it would be X spin left, for example, and then we get another Z analyzer that does Z spin down, it would turn out that the subsequent X analyzer would measure it to be X spin to the left again. In other words, it just duplicates the initial X spin measurement outcome. Okay, let's just pause a quick second to reflect on what these experiments actually say, because so far it seems kind of strange, but doesn't seem really, really strange. What I'm going to try to convince you of is that things are very, very strange if you actually reflect a little bit closer upon what we're observing here. What's really strange is that if you look carefully at both experiments 6 and 7, so just consider, for example, experiment number 7, it turns out that this experiment, if you think about it, demonstrates that there is no fact of the matter as to whether or not the electron took exactly a Z spin up trajectory prior to entering into the second X analyzer, or whether it took a Z spin down trajectory entering the second X spin analyzer. Now you might ask, well, how is that possible? After all, it had to have entered into the Z axis analyzer after the first X spin measurement. And that's right in a certain sense, but suppose, after all, there's only going to be two different cases. Suppose the first case, which is that it did take a definite Z spin-up trajectory prior to it being measured at the second X spin analyzer. In other words, look at situation number 7 and presume that it in fact took that particular trajectory prior to measurement. If it were the case that it had a definite Z spin-up trajectory, then it would be such that, in accordance with the previous experiments, experiments 4 and 5, it would turn out that if we took this very seriously, that it had a definite Z spin-up trajectory, that when it enters the last X spin analyzer, that is the second X spin analyzer mentioned here in experiment number 7, that you would not get with 100% probability the measurement to be X spin to the right. Why not? Because after all, remember, the more precisely we can know the Z-axis direction, the less precisely we can know the X-axis direction. In other words, if it was truly the case that it was Z spin up prior to entering into the X spin analyzer, that the probability of it being detected X spin to the right would actually be 50%, not 100%. That is, you'd get some electrons heading to the left as well. But that's not what we observe. And again, consider the case in which the Z analyzer was such that the electron was measured Z spin down instead. Well, if it was measured Z spin down, again, all that matters is that there's a determinate Z spin outcome. And if there were a determinate Z spin outcome, then you would again observe at the second X spin analyzer that there would be a 50% probability of it being measured X spin to the left and 50% probability of it being measured X spin to the right. But again, this is not what we observe. What we observe is with 100% probability, the electron will be measured X spin to the right if it was initially measured X spin to the right. Two other possibilities remain. One is that, well, what if it took both trajectories? What if somehow the electron went both Z spin up and bounced and hit the north wall, and it somehow also, that is, even though it's a single electron, it somehow paradoxically took two different positions simultaneously. Again, that wouldn't be what we would expect from the 100% x spin right result. That is, if it took both trajectories, that meant it still had a 100% probability, that is definite z spin direction. That is, it had z spin up and z spin down. And so long as one of those two things is with 100% probability, in fact, in this case, there's both up and down are going to be 100% probability by hypothesis, that it would turn out that if you were to enter into the x spin analyzer, you get 50% probability x spin left and 50% probability x spin right. But again, this is not what we observe. We observe with 100% probability entirely x spin right results. So that means, summarizing very briefly, the electron could not have been definitively z spin up, and it could not have been definitively z spin down, nor could it have been both definitively z spin up and definitively z spin down. Instead, we have to conclude that there was no matter of fact as to the z spin outcome of this electron prior to being measured. As if things couldn't get already so confusing and complicated, it turns out that observer-dependent effects are quite important to understanding the empirical results of quantum mechanical phenomena. So again, in this result, an experiment, notice that we have, as usual, the silver in the annealing oven on the far left-hand side, heated up to about 1300 degrees Celsius, and we have electrons being shot out of the electron gun on the side of the annealing oven. So as electrons pass through the inhomogeneous magnetic field, enter into the Stern-Gerlach apparatus that is measured in the x-axis direction, we isolate all the ones that were x spin to the right, and then it enters into a subsequent z-axis analyzer. And here in the z-axis analyzer, again, we have 50% probability of them being measured z spin up and 50% probability of them being measured z spin down. So in this particular experimental setup, suppose it were the case, as I've illustrated in this diagram, that it was 100% probability z spin up. And suppose that it also turns out that there is an observer, which I've illustrated with this little stick figure, saying, hey, I'm watching for electrons, and I'm here to check out whether there's any electrons. And the observer is specifically looking at this area that I've circled in green. And the observer's thinking to himself, weird, I don't really see any electrons. There are no electrons here. Okay, that doesn't seem too bizarre. After all, by hypothesis, the electron has traveled the z spin up direction in this particular context. Well, what's really strange about this is that the observer, even if the observer is there, observing empty space where there are no electrons, it turns out that this is sufficient for there to be a fact of the matter as to the location of the z spin, contrary to experiment number 7. Now, I'm not saying it's inconsistent with experiment 7, that is the previous experiment. I'm simply saying that it is different in a very subtle way. So here we have an observer observing the absence of a particular trajectory that the electron took. So if it turns out that the electron was not observed here, we know with probability 1, it must have been registered as z spin up when it entered into the z-axis Stern-Gerlach apparatus. In which case it assumes a definite spin measurement, bounces off the north wall, and then when it enters into the final x-axis analyzer, because it has definite z spin up, we observe, as you would expect for a electron with a definite z spin up measurement reading to have when it enters an x spin analyzer. Namely that there's 50% probability x spin to the left and 50% probability x spin to the right. And the reason that I've circled this in red with the question marks is because this is very strange. That is, to remind you again, the observer here is observing absolutely nothing whatsoever. The observer is watching for electrons. They do not detect electrons, and that is sufficient to, so to speak, collapse the wave function such that the electron assumes a definite z-spin outcome, which is z-spin up in this example, and that forces the quantum statistics to turn out 50%, 50% when it enters the final x-spin analyzer. This is different than experiment number 7, which I mentioned previously, because in that experiment there was no observer. And because there's no observer, there is no fact of the matter as to whether or not the electron was Z spin up or Z spin down prior to being measured into the next x-axis analyzer. Okay, so now that we've described the history of the Stern-Gerlach experiments, we have to discuss the Einstein-Podolsky-Rosen paradox. So in 1935, Albert Einstein, the very famous physicist, got together with fellow physicists Nathan Rosen and Boris Podolsky at Princeton University's Institute for Advanced Study. And the argument of their paper was essentially as follows. So I'm going to add a modern spin to this. Forgive the pun. The pun is not intended there. I'm going to add a modern spin and twist to this by considering an analogous result to what they showed using what's called the neutral pi meson. So a neutral pi meson is a particular kind of subatomic particle, which I've illustrated here with the Greek letter pi to the power of 0. And it turns out that this is somewhat of an unstable particle and that it can decay in certain circumstances into an electron, which is e to the negative, and into a positron, which is represented by e to the positive. Okay, so to quote from David McIntyre's excellent textbook, Quantum Mechanics of Paradigms Approach, an unstable particle with spin 0 decays into two spin-half particles. Spin-half particles here are the electron and the positron, which by conservation of angular momentum must have opposite spin components, and by conservation of linear momentum must travel in opposite directions. Okay, so looking at condition number 1 for the EPR paradox in the top left-hand corner, in this setup, spin measurements are perfectly anti-correlated. So what is meant by anti-correlated here is that we have the electron shooting off to the left, and we have the positron shooting off to the right. And the neutral pi meson is in the box in the middle decaying. And so when the decay process occurs, they shoot off into opposite directions given the conservation of linear momentum. And given the conservation of angular momentum, we know that if we were to have a Stern-Gerlach apparatus measured in the z direction on the left side, that when the electron enters, if it were to be measured, for example, z spin up, then we would know, because it's entangled with the positron on the opposite side of the experimental setup on the right-hand side, that the positron's z spin value will be measured z spin down. And it's very important here that in this particular case, the distances between the Stern-Gerlach apparatus and the neutral pi meson's chamber in the center can be arbitrarily far away from each other, and this will play a pivotal role in just a moment. So the reason I've drawn the red arrow again is just to represent the fact that if there was to be measured a z spin up for the electron on the left-hand side, then we would have exactly anti-correlated results with a z value for the positron in the z down direction. And analogously, if it were to be the case that the electron assumed a z spin down direction, then we'd get a positron reading of a z spin up measurement result. The second assumption in the EPR paradox reasoning is that the correlation of both spin measurements is independent of measurement direction. That is, assuming that the same direction is measured for both particles. If one can measure particle A's, that is the left side Z component with spin, and record Z spin up, then we know with 100% certainty that B's right side will measure Z spin down, given perfect anti-correlation. At step 3, EPR introduced what's called the reality criterion, which is a key assumption in their reasoning. To quote, because we can predict a measurement result with 100% certainty in certain circumstances, that result must be, to quote, real property of the particle. It must be an element of reality. So the thought here is that if it is actually going to be the case that once we make a Stern-Gerlach z-axis apparatus measurement for the electron on the left side, that determines the z-spin value. After all, we knew from the previous few experiments in the Stern-Gerlach experiments that there is no fact of the matter prior to there being measurement. So in this case, if we were to make the measurement, and that will be stochastically and randomly determined after all, but once we make the measurement, it will produce a definite result. And that definite result will be z-spin up or z-spin down. And once it becomes measured z-spin up or z-spin down, that will instantaneously affect the value of the spin value for the positron on the other side, on side B. And that, again, will be anti-correlated. So the thought here of EPR's reasoning is that, well, if we can say with 100% probability that if it is Z spin up on the left side, then it must be Z spin down on the right side. And if it's Z spin down with 100% probability on the left side, it must be 100% probability Z spin up on the right side. Then there must be some real property of the particle, namely its spin value, that obtains prior to measurement. So this is what is being explained in step 4 here. Since A could be measured in the x, y, or z axis directions, it follows that the spin values for particle B are not only perfectly anti-correlated, but must exist prior to measurement. Step 5 is where the locality assumption enters. That is, physical information, as to be distinguished from physical causes, which I'll explain in just a moment, can only happen locally. That is, they cannot travel faster than the speed of light. So what's the distinction here between information and causation? Well, according to the definition that we are going to use, information with respect to a physical system obtains only if we are capable of intervening upon that system in a way such that we could communicate information from that physical system to another physical system out of our own will, so to speak. Now, when I say out of our own will, this does not presuppose the nebulous notion of free will. Rather, it is only to say that causally intervening upon this particular system allows us to have some choice in some sense of the term of influencing other physical systems. Now, we know from special relativity, which is a well-confirmed and empirically accurate scientific theory that has been defended by Einstein in the early 20th century, and we know from numerous laboratory experiments that information, as defined as I just said it, cannot travel faster than the speed of light. That is, you cannot causally intervene on systems in such a way that you can influence the results in very specific ways. What turns out is superluminal, however, is physical causation itself in a certain restricted sense. In what sense is it possible for there to be physical causes that transcend the speed of light? Well, recall again that in the neutral pi meson case, if it were to decay into an electron heading to the left and a positron heading to the right, that once you were to measure with a Stern-Gerlach apparatus in the z-axis direction, the z-spin value of the electron, let's say on the left-hand side, that instantaneously induces a definite z-spin for the positron on the right-hand side that is perfectly anti-correlated. It is specifically in that sense that causes can obtain superluminally, but that information cannot. Why can information not be transmitted in this particular EPR paradox setup? Because we cannot choose whether or not, in fact, the electron or the positron initially assumes a Z spin up or Z spin down. That is random, and that is stochastically determined. All we can say that isn't random is that once we measure whatever that result is for the electron or the positron, we know that the opposite entangled particle will have an anti-correlated spin result. That is, it will be the opposite spin result. Okay, so step number 6 says that the orthodox Copenhagen interpretation, which is what we're working with in this discussion, that the orthodox Copenhagen interpretation of quantum mechanics states that there do not exist physical properties prior to measurement. And so the claim is that, well, quantum mechanics either shows that nature is intrinsically non-local, or that quantum mechanics is incomplete. After all, as we knew from the reality criterion previously, and as we've walked through these examples, if we can say in a certain sense that once the measurement is made on the electron, suppose, on the left-hand side, that we can say with 100% probability that the positron on the right-hand side is going to have the exact opposite spin measurement result, then we can say that there does exist some fact of the matter prior to measurement. But if there does exist some fact of the matter prior to measurement, then it follows that in some sense quantum mechanics is incomplete. That was the conclusion that EPR arrived at, as you can see in bullet point number 8. So the thought here is that quantum mechanics is incomplete insofar as it's possible for there to be a hidden variables theory. That is some kind of theory that contains all these hidden variables that accounts for our ignorance about the initial conditions of the system. That is, orthodox quantum mechanics cannot tell us deterministically whether or not their spin values are going to be up or down prior to measurement, but perhaps EPR claimed there could be a hidden variables theory that also preserves the locality of which physical information cannot transfer faster than the speed of light. Well, it turns out that those hopes were thwarted by the work of John Stuart Bell, the eminent Irish physicist. So, looking at bullet point number one might try to improve quantum mechanics by positing what is called a local hidden variables theory. That is, amend the deficit where we can't know conjugate variables values simultaneously by introducing a hidden variable. So it turns out that this isn't possible. It turns out that Bell's theorem, which he proved in 1964, is that it is not possible on pain of, in some sense, mathematical contradiction and empirical refutation, that is, it is empirically false, that we could have a local and hidden variables theory. We must give up at least one of these two desirable properties. So before we get into Bell's theorem, it's important to note some common confusions of which I myself also was confused about prior to learning about this. Common confusions about what Bell's theorem says. For example, some people think that Bell's theorem shows that there cannot be any hidden variables theory of quantum mechanics whatsoever, but this is arguably incorrect. In fact, in light of his own result, Bell himself actually advocated a non-local hidden variables theory, which if you look again at bullet point number 2, you'll see is consistent with Bell's theorem. In fact, he advocated a non-local hidden variables theory of the kind that was defended by the American, eventually turned British, physicist David Bohm, of which he defended in 1952. Hence, it is not true, and this is why I've underlined this, because again, it is a common confusion that some people get, that there cannot be any hidden variables theory of quantum mechanics. Bohmian mechanics is one such theory. It's just peculiar in that it is non-local, which, don't get me wrong, is certainly undesirable, but it's beyond the scope of today's discussion to describe why non-locality is such a peculiarity. And for those who want to read more about this, you can consult the source at the bottom of the page, namely Tim Maudlin's paper, What Bell Did, published in Journal of Physics A, Mathematical and Theoretical. Okay, so on to Bell's theorem and the reasoning that he used. We're going to consider a slight amendment to Bell's original result because this will be a little bit easier, at least I hope, to understand. So we're going to follow the presentation in David McIntyre's 2012 textbook, Quantum Mechanics, A Paradigms Approach. The step one is to first consider two particles as in the EPR setup in three directions, A, B, and C, in a two-dimensional plane, each 120 degrees from each other. So you can see that both on the left-hand side of the EPR setup and the right-hand side. The second step is, since it's an EPR setup, spin measurements can only be up or down along each direction. So we're just going to denote this simply with a plus or a minus. So whatever the hidden variables are, they must be anti-correlated with each other. Why must they be anti-correlated? Well, the reason's because, again, we have to make sure that the results of quantum mechanics are consistent with the empirical data that we observe in laboratory settings. That is, we allow the advocate of a local and hidden variables theory to choose whatever hidden variables they like, so long as they cohere with experimental results. So we can represent the dictates of the hidden variables theory by assuming that there are instruction sets as above. So I'm just using one example. We'll go through a few more examples in just a moment. But here is one example that I've illustrated. So again, consider the case where there's a neutral pi meson that decays into an electron and a positron, and the electron shoots off to the left and a positron shoots off to the right-hand side. Suppose further that the choice of measurement directions are A, B, and C on the left and A, B, C on the right, and suppose that it turns out, again, this is stochastically and randomly determined, but suppose it turns out that the electron heading to the left-hand side, when it hits the A-axis here, is measured A spin up. Then we would know for a fact that the entangled particle, that is the positron heading to the right-hand side, would have to have a spin down value. After all, they're perfectly anti-correlated with each other. So that's why I've drawn a red arrow next to the A on the left, heading in the upwards direction, and a red arrow on the right-hand side next to the A heading in a downwards direction, because they're anti-correlated. Similar results also happen for B and C. That is, if you were to measure the electron in the B direction, suppose that it were to be measured B spin down, then it would be B spin up on the right-hand side. And lastly, for the purple arrows as well, you get anti-correlated results. Step 5 is to start doing some combinatorial reasoning. So combinatorics is just the area of math in which we consider different combinations of possible states of affairs and enumerate the different possibilities that could occur. So there are going to be 9 different possibilities of measurement directions between both sides. Why 9? Well, you could measure both sides being A, the left side being A, the right side being B, the left side being A, the right side being C, left side being B, right side being B, left side being B, right side being C, C, A, C, B, and C, C. That makes 3 choices for the left of A, B, or C, and 3 choices for the right, of which, of course, 9 is equal to 3 times 3 in that sense. Now, for each of these measurement setups, there are now 8 different instruction sets that describe the arrangement of the hidden variables. So why are there going to be 8 different instruction sets? Well, we have 2 choices for A. That is, there could be spin up or spin down, 2 choices for B, and 2 choices for C. And in this case, 8 is going to equal 2 to the power of 3 because, again, there's 2 choices for A, 2 choices for B, and 2 choices for C. And so if you work out the combinatorics, there's going to be exactly 8 different choices. And so if you have a look at the table that I've drawn here underneath the EPR experimental setup, we have a table that lists 8 different possible particle types. So when I say particle 1, I mean a particle that is detected on the left-hand side, and particle 2 is a particle that's detected on the right-hand side. Under the heading population, we have N1, N2, N3, all the way through N8. All that means is going to be the number of particles that have the particular value. So the number of particles, for example, that are of type 1 will be listed N1. The number of particles of type 2 will be listed N2, and so on and so forth. So those would be constant numbers, and we allow those numbers to vary depending on the experimental setups. So how do we get these exact 3-vector values that we see listed in the table? For example, why do we have under particle 1 in the top row A plus, B plus, C plus, A minus, B minus, C minus under particle 2? Well, the reason is, again, because there are going to be 8 different possible instruction sets that could describe the arrangement of the hidden variables that are nonetheless consistent with the empirical data. Remember, they must be anti-correlated. To see the anti-correlation, notice that, for example, on line 1, we have A plus, B plus, C plus, and that we would know that if there was going to be measured up spin results along A, B, and C, there must be down results, that is minuses for particle 2 on the right-hand side. So if you just look at the table closely, you can see that the different arrangements are as they're stated. But let's go through a little bit more detail so this becomes really clear. Consider instruction set number 2, for example. The set of hidden variables consistent with the empirical data are going to be as follows. So look on the left-hand side, we have a list here of different pluses and minuses circled in black. So how did I come up with these particular instruction sets? Well, look very carefully at line number 2. Line number 2 says, under the heading particle 1, it says A plus, B plus, C minus. Under heading of particle number 2 is listed A minus, B minus, C plus. Now let's work out the 9 different possibilities. Remember, we said that there's going to be 9 different possibilities. What are those 9 different possibilities? Well, we have A plus matched with A minus. That is, consider the first of the 3 numbers, or letters, excuse me, under particle 1 with the first of the 3 letters on particle 2. And then we're going to match the first of particle 1 with the second of particle 2, which gets us the second result. And then consider also the first on particle 1 with the third result under particle 2. So you get A plus A minus, A plus B minus, and then A plus C plus. And that's why if you look on the far left-hand side of the slide, you'll see that we have plus minus, and plus plus, because that represents A plus A minus, A plus B minus, and A plus C plus. And so we continue in this fashion for the next set of 3, which is going to be considering the B plus particle under particle 1 and its measurement value in relation to the measurement values under particle 2. So we're going to consider B plus A minus, B plus, B minus, B plus, C plus, which is what you get for the instruction sets and the hidden variables listed on the far left. So we get for number 4, 5, and 6, plus, minus, and plus, plus. And lastly, you get minus, 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 and minus, plus. So if you actually work out the combinatorics for all of these different 8 possible particle types, what ultimately arguably matters when you look at the data is whether or not the probabilities are same or different. At least this is what will matter for Bell's theorem. So if you work out again the combinatorics for each instruction set, we get the following statistics if you look on the left-hand side. The probability of getting opposite will equal exactly 1. That is, with 100% probability you get opposite spin measurements in the hidden variables instruction sets for types of particles 1 and 8. For types of particles 2 through 7, you'll observe that the probability of getting opposite results is 5 over 9, and the probability of getting same spin results is going to be 4 out of 9. You might ask, well, how did we get those numbers? Well, look again at the instruction set for number 2, that is of particles of type 2 on the second row in the table. So I've drawn this with a red arrow here. And look again on the far left-hand side. What are the number of particles that were listed to be opposite? Well, there's going to be 5 of them. That's why we have 5 different measurement readings that are listed opposite. And we have 4 different measurement readings that are circled in green that are listed the same. So that explains the statistics for getting the probability of opposite being 5 over 9 and probability of same being 4 out of 9 for particles of types 2 through 7. So in order for us to determine the probability of same and the probability of opposite for all of the different experimental types, we have to calculate what's called a weighted average over all particle types. So what's going on here? Well, have a look at the following, what are called Bell inequalities. At the very top here of the 4 different inequalities we have the probability of same equals the following. 1 over the summation of n sub I, from where I is an index going from 1 to 8, times 4 out of 9 times n2 plus n3 plus n4 plus n5 plus n6 plus n7, less than or equal to 4 out of 9. So what's going on here is that the reason that we have 1 over sigma sub I n sub I is that this is supposed to be a weighted average over all particle types. And here, all these n numbers are supposed to represent the population. That is, the actual number of particles that are going to be within the particle types n sub I. So n2, for example, is the number of particles of type 2, n sub 3 is the number of particles of type 3, and so on and so forth. Now you might ask, well, how did we get this inequality? How did we get the top inequality, for example? Well, that follows from the third inequality. The third inequality, I hope, is a little bit more lucid. The third inequality is exactly the same information as is the top inequality. That is, it surely must be the case as a matter of simple mathematics and of the definitions that we have given, that 4 to 9 times n2 plus n3 plus n4 all the way to n plus 7 must be less than or equal to 4 to 9 plus all the population numbers for the index running from 1 all the way to 8. After all, in this case, n sub I, that is, all of the population numbers must be positive numbers of some kind. So this just follows immediately. Now you might ask, well, how does the second of the 4 Bell inequalities follow? So here we have a different inequality. We have the probability of getting opposite across all different particle types is going to be 1 over sigma sub I, n sub I, times n plus 1 plus n sub 8, plus 5 over 9 times n sub 2 all the way added to n sub 7, which will be greater than or equal to 5 over 9. So this follows from the fourth line. That is, the fourth inequality is identical to that of the second inequality. And again, this just follows by simple arithmetic and the definitions of population particle types that we've given in the previous slide. Okay, so just quickly summarizing again, to see why these Bell inequalities follow mathematically, just multiply both sum and coefficients and remember that probabilities must sum to 1. And the last step before we get to the conclusion is that, well, it turns out we actually have robust experimental evidence that the probability of same is equal to the probability of opposite, which equals 1 over 2. That is 4.5 over 9. Now, if you look very carefully at what this means, that means that the Bell inequalities are violated. After all, we know from experimental data that the probability of same equals the probability of opposite, which equals 50%. And that violates both the probability of same and the probability of opposite Bell inequalities that are listed in lines 1 and 2. After all, if probability of same is equal to 1/2, that would equal 4.5 out of 9, which is clearly not less than or equal to that of 4 over 9. Similarly, if probability of opposite actually equals 50%, that is 4.5 out of 9, that's clearly not greater than or equal to 5 over 9, which is what the Bell inequality suggests. So the conclusion is that assuming that there was a local and hidden variables theory, we would be led to a mathematical contradiction and empirical refutation from data from experiments. Therefore, there cannot be both a local and hidden variables theory. That's what Bell's theorem says in a nutshell. Okay, so quickly wrapping up what we've discussed today. Quantum mechanics is one of the most empirically supported and accurate theories humans have come up with. This is not hyperbole. Quantum mechanics is difficult to make sense of conceptually, as we can see from the puzzles that the Stern-Gerlach Apparatus experiments and the EPR Paradox raises. Quantum mechanics fundamentally challenges pre-quantum era conceptions of physical reality. Quantum mechanics has several empirically adequate but distinct interpretations: Copenhagen, Bohmian, Eveready, many worlds, GRW, etc. Unfortunately, it's beyond the scope of today's discussion to talk about these alternatives, but we did briefly mention Copenhagen and Bohmian. After all, Copenhagen is the mainstream interpretation that we've been working with over the course of our discussion today. Quantum mechanics is not a final theory of nature. After all, it's non-relativistic, and it faces the notorious measurement problem, among other issues. There are more empirically accurate theories than quantum mechanics, specifically when it comes to subatomic particles, namely quantum field theory. But again, it is beyond the scope of today's discussion to get into quantum field theory. Lastly, quantum mechanics' mathematical formalism is well understood. So despite the conceptual confusions that quantum mechanics raise, we know that quantum mechanics is mathematically well understood, it is empirically accurate and empirically supported, and yet it raises many, many puzzles about the nature of physical reality. And that's it for today's discussion.